Hello everybody, and the lesson today I want to show you how to fill NANs in with predictive values based on a couple different machine learning methodologies here. So I'm sure you're going to see this in your data science career and your machine learning career at some point. If not, you already have. Probably you've seen this a long time ago, right? So how do we deal with nulls? You can fill nulls with NA. You can fill nulls with 0. You want to get rid of the NA or the NAN. You can fill those with mean, median, mode. You can backfill, forward fill from the most recent number or the next in line number. So there's a variety of ways to do that, but that doesn't always give you the most closest approximation for the number. It just happens to be the mean or the mode number or forward fill. That can be somewhat dangerous. It gives you more insight because at least you don't have the 0. You have something in there, but how representative is that number of the actual number that's missing? That's kind of questionable, right? We don't really know. No one can really say for sure. So dealing with nulls is kind of a kind of a nuisance, but we have to do it. We have to find a way to do it. So this is one of the most accurate ways to do that. And if you don't want to use any of these options that I described, you can always drop the record. But as you drop more and more records, if you have a bunch of nulls, now you have a lot fewer records to train your model over. And with fewer and fewer records to do the training, the model might not learn the nuances of the model. It might it might not be able to make accurate predictions. It might make really weird, inaccurate predictions. It might be overfit, it might be underfit, right? So we want to try to get the numbers filled in as accurately as possible, and there's a couple of ways to do that. So let me go ahead and load data that I have from the canonical Titanic dataset. I'm sure you've seen this at some point. This is a bunch of data relevant to the first voyage of the Titanic, coming from Europe over to New York City. Everybody knows the story, right? Here's the data points that were captured from that trip. So we have survived. This is the binary number, 0, 1, passenger class, 1, 2, or 3, the gender, age of the person, so on and so forth. First, second, third class, was it man or woman? That's kind of redundant, right? We don't need the class because we already have the sex. I think we would actually drop one of those. Otherwise, we have like highly redundant data, but that's not what this video is about. I just saw that right now. I'm pointing it out. So we want to look for nulls and then be able to fill in these nulls. So there's an easy way to plot all the nulls. We can count it as well. I'll show you how to do both. I think a picture's worth 1,000 words. They say that in most of my videos. So you can see here, most of these blue numbers are filled in, so they're not missing. Let's go down a little bit, but there's a few from the H feature group that are missing, and there's a whole bunch from the deck group that are missing, right? So I'm kind of concerned about the deck group, and age looks like maybe 1/3. The deck looks like mostly missing. Let's look at let's do a quick numerical count. There's the visual. Here's the numeric quantitative result. So if 869, 688 are missing, that's a pretty big number, right? So that's a major concern. 177 out of 869 are missing. Less of a concern, but still, I mean, the age can be anything, right? It can be all over the place. If that was a gender feature, maybe it wouldn't be so concerning. It could be just a male or a female. But with the age group, it could be anything from a toddler to a pretty senior person. So we would like to get those filled in and make this data set as comprehensive and as complete and as meaningful as possible, right? So let's get the independent variables and use that for our X variable here. These are our independent variables, and we have a dependent. This is going to be age. So we know that we're missing records in age. We're going to try to backfill that age group. We're going to use a linear regression model, okay? And based on all the features that we see in survived, passenger class, SIBSP, not sure what that is, I'll be honest with you, and PRCH, again, not quite sure what that one is, and the fare, that's how much they paid to get on the boat. Doesn't matter. These, we have enough data for them, all filled in. These are pretty much comprehensive and complete as far as we can see in this view over here. So it doesn't matter what the features are. As long as they're not missing, we can use those to predict what this Y variable should be. These are the missing features right here. So we're going to use a linear regressor and go ahead and run it. Control Enter. Look at the R squared. Okay, r squared 0.1304. So if you don't know anything about r squared, I'll educate you right now. This is a horrible r squared. We want close to 1.0, at least high 9, at least 0.9 or something like that. 0.13 is basically useless. That means in about 13% of the cases, the model is making an accurate prediction. About 87% of the time, it's wrong. That's a huge number of wrongs. We can't deal with that number of wrongs. So we have to come up with a different approach. We are going to look at training data for X and training data for Y. We are taking these values and then fitting that into the linear regression model. Here's the training for X, training for Y. And then we are going to make a prediction. Linear regression, that's the model. And the property is to predict test data. Okay, and we want to backfill this into age. So I'm using this variable as age. So this is a very generic example, but you can use anything in your data set. That's my hope, is that you can load a data set, use your specific missing value. In this case, it's age. It could be anything, right? Anything you're dealing with specifically. Set that as the target variable and just copy and paste the rest of this. This should be pretty scalable, pretty flexible. It should work in pretty much any case I can think of. Okay, so let's see what happened here. Now the age is backfilled, so we had 177 missing, and now they're all there, and we're printing out the ages right here. So it looks a little bit weird in this view, but you can see that there's no blanks. Everything is filled in. And this is a common delimited list. Okay, so all the ages are filled in. Survive, P-class, Parch, Fair, Age. So we're good to go there. Let's do another linear regression. And hit Control Enter. Let's see what the R squared is. All right, this is very nice. So we went from 0.13 to 1.0, so we got perfect prediction. So that's one way to backfill missing data in your data set pretty quickly, pretty simply, very easily, and be able to make predictions into the future that are 100% accurate. So that had a pretty good outcome there. Now let's look what's in my notes, and just looking at this, I haven't checked this out in a little bit. Let's try to impute missing values that are objects and non-numeric. Okay, so that was a numeric, right? Object was age, or whatever, the feature was age. So numerics and non-numerics are very different. A non-numeric is considered a label or a categorical code or a label encode. That was originally a label and encoded into numerical data. Numerical type of data is 1, 2, 3, 4, 5. It's continuous. It could be the temperature would be a numerical continuous feature. Okay, it could be 70, 71, 72, 73, 73 and a half, 74. But the weather condition, like sunny, rainy, hazy, cloudy, snowy, those would be labels. So that would be categorical data, right? So numerical data and categorical data are very different. Let's do a similar experiment on categorical data. We just saw the numeric data. Let's look at categories now. So this is more of a classification type of problem. Again, we are going to do a quick sanity check on the data. Okay, everything's okay. We filled in our age, so that is fine now. Oh, we only have the age. Okay, we're looking at deck. Okay, so the deck is a category, and it's not numerical; it's a label. So we have to handle this a little bit different. We have to assign categorical codes. You can do label encoding, one-hot encoding. I prefer categorical codes. If you have a lot of features that are high cardinality of high cardinality type, that would mean like a whole bunch of male names, female names, names of United States, names of all the counties within the United States, and you take that and assign a numerical value to each one. That's a lot of numbers. If you can store that in one column as a categorical code, you just have one column. If you do one-hot encoding, you're going to create dozens and dozens, sometimes hundreds or maybe even thousands of new columns, and you probably don't want to do that. I think categorical codes are probably the easiest to work with. The alternative would be label encoding, but I would recommend to avoid one-hot encoding. That just creates high-dimensional data, and it gets very difficult to work with, right? So now we are taking, again, independent variables and looking for the dependent variable. Again, this is a label now. It's not a number. This is a label deck I don't even know what it looks like. Upper deck, lower deck. Let me go back and get a quick idea of what this is. Deck. Oh yeah, so you can see all the NANs. You can see it right here. Deck C, deck B. Oh, I guess they had like an A, B, C, and then we had a bunch of NANs, okay? So perfect. We are going to go ahead and fill in those NANs and going to run this, see what the result is. 72, again, closest to 1 is best, 0.9, high 9s, that's what we want. That is 72. This is going to be r squared 0.70, so it's okay. It is statistically significant, but just barely. Let's look at this one. We want to see like at least a high 9, preferably. 72.6, so slightly better, but still coming up a little bit short of high 9s or 1.0. That would be ideal. Okay, but let's go ahead and try to use a random forest classifier to solve this problem. We're doing a fitting with the train and the Y train, the X train, and then the prediction down here, and then we're trying to get the accuracy. So the accuracy turns out to be 0.78. So it's increasing a little bit with a different classifier. Now we have K and N classifiers, so we're trying to a couple different modeling techniques here, or a couple different models anyways. Okay. Run that, and now we're down to the training, again like we saw with the regression model, the training for the X, training for Y, right there and right there. We fit the model right here, and then Control Enter to run it. Okay, find any missing data points. Let's keep going. Okay, here we are printing categorical codes. Okay, check for nulls. And then, okay, we got the deck filled in. So now all of the missing numbers, we had a bunch in there, like 688 or something. Now we're down to 0, so that is excellent. Let us rerun this random forest classifier before we're getting 0.7 or 0.72. It was pretty dismal r squared number. Now we're getting 0.95. So look at that. We went from a low r squared to a pretty decent r squared, 0.95, 95% of the time we're making accurate predictions. I'm pretty thrilled about that. We had 1.0 with the regression model, 0.95 with the classification model. So there we go. We imputed missing values using a couple different machine learning techniques. We had the regression models, we had the classification models. So I would say this is a success. One more thing we'll look at here, I think, is another heat map. Let me refresh this to get the view. And this looks like the original heat map. Okay, so I think one small piece of code is off. Because right here, I'm seeing all those decks were filled in. I think that there might be a small bug in the code or something, but we went from 0.78 to 0.95, so I would say that's an overwhelming success. I hate to admit it, I think there's a bug in the code somewhere, or we're plotting the original chart all over again. I'm not sure what happened there. Or one of the data sets was misnamed. Anyways, let's continue on. I haven't looked at this case in quite some time. Okay, here's the scale data. So we're taking it and scaling it from 0 up to 1. So that's what the scaler does right here. If you're working with data that has a lot of outliers, it's good practice to scale the data to get it all consistent and conforming within a certain range of data points, 0 to 1. And it can be distributed anywhere within that, but you don't have these extreme outliers like 1 to 1,000 and you have a couple of records that are a billion. It would take those billions and squeeze it into a range that fits within 0 to 1. Okay, so that's what the scaling is doing. And then just reading through my notes here, K and N imputer. Oh, I think this is, yeah, one more way of doing it. Instead of using like the traditional machine learning models, there's a K nearest neighbor imputer that does the lift for us. let's see. Okay, yeah, so everything is 0 now. So that's one more way, without using a traditional classification model or traditional regression model. There's actually a KNN imputer model in the sklearn library that actually does the imputation for us. I haven't looked at this in a while, so I forgot about that last part of the case study. But there you go. So we got everything down to 0. Our model is trained, tested, making accurate predictions. In the regression area, it's 1.0, so basically perfect. In the classification side, it is 0.95, so close to perfect, 95% accurate. And this example, I think it's good enough. It's just a fun example to illustrate how to fill in NANs using some imputation techniques. So that's it, everybody. I hope you learned something new today. I think this stuff is pretty cool, pretty interesting, very useful, and just overall, like, yeah, it's pretty neat to work with this data, and you can do some really remarkable and quite tremendous things. So that's it. That's how you fill NANs with predicted values. I gave you three solid examples, and we had some pretty good outcomes there. So that's it. Thanks for your time today, guys. Have a great day. Bye.